let me pull it up. So,
The stuff you're going to be able to verbalize to me?
yes, I'm just trying to find my little packet thing.
Okay. The only thing I can say is you're better off in Florida than Colorado today.
Why?
We got 1.5 feet of snow today.
Oh, that's not fun.
I've been shoveling all day.
Okay, so we are on Pythagorean Identity.
Okay.
And different and like the problems having to do with reference angles and quadrants.
Okay. First of all, there's 3 Pythagorean identities. Do you know what they are without looking at the paper?
A squared plus b squared equals.
Well,
no.
This is the first one. Sine squared plus cosine squared equals 1.
Oh, and then 1 plus cosine squared equals...
Next one has tangent in it. And you're correct, it's tangent of x plus 1 equals secant squared. Now these are really the only 2 you have to memorize. There's a third one. But there's an easy way to figure out the third one. The third one is the same as the second one, only using the cofunctions. So what's the third one?
Cotangent plus 1 equals cosecant squared.
Exactly. So really, if you memorize the first 2, you can always figure out the third one. But those are the only 3 that I know of.
All right, wait. Where is my...
That's regardless of the angle. In other words, if you try some of these, you'll notice the sine of 30 degrees squared plus the cosine of 30 degrees squared does indeed equal 1. Always. No matter whether it's 30 degrees, 29 degrees, 89 degrees, doesn't matter.
Solving for,
Would it be easier if you took a quick picture of it and sent it to my email?
No, I can't find it. I have it. I know I have it with me.
Okay.
I gotta find it.
Usually the only problems that have to deal with Pythagorean identities are verifying trig identities or solving trig equations. In other words, where you actually have to make the substitution. When you see sine squared plus cosine squared, you substitute 1 for it. And that facilitates the solution.
Some of the other questions we got, though, were like, what is the reference angle of, like, let's say 30 degrees?
Okay. 30 degrees is in the first quadrant. Okay, right. That's quadrant 1, 2, 3, 4. So the reference angle is always the angle made with the x-axis.
Okay.
Okay, so if 30 degrees, the reference angle is 30 degrees. But if you said 120 degrees, well, that's different. That, I go around 90, I go another 30, there's the ray. In other words, there's my 120 degrees. What's the reference angle? Which is always the angle made with the, I should rephrase that. It's always the acute angle made with the x-axis.
So would it be 60 degrees?
Correct. And so the reference angle is always 180 minus theta in the second quadrant. And what if I said 210?
210 is
Now,
past 180.
well, halfway would be 180, right? That's 180. That's 90. That's 270. So 210 would be like to there. In other words, if that is 210, what's the acute angle made with the x-axis equal to?
65.
30. In other words, it's 210 minus 180, right?
Okay, so it's x-axis.
So it's really theta minus 180. In other words, these little tricks here for knowing what the reference angle is, those end up becoming absolutely critical, because this is what you end up using for any angle greater than 90 degrees.
So in the first quadrant, it is theta.
It is that angle, right. In other words,
in the second, it is 180 minus theta.
Right.
Equals theta.
In the third, it's theta minus 180. Notice that when my angle was 210, it was 210 minus 180, and that gave me 30. That was my reference angle.
And then in the fourth quadrant, it would be...
It's the same as the second, only it's 360 instead of 180.
Okay. So 360 minus theta.
Right. So no matter what angle I give you, let's say I give you 300 degrees, what's the reference angle?
If you 60.
Correct. Let's say I gave you 225, what's the reference angle?
225 would be 45.
Correct. In other words, the first thing you do is spot what quadrant it's in, and then once you have the quadrant, you use one of those formulas. And that reference angle always is going to give you the same trig function as the first quadrant would. In other words, if I'm looking at a reference angle of 30 degrees in the third quadrant, its trig function is the same as 30 degrees in the first quadrant. The only difference might be its sine. In other words, have you heard all students take calculus before?
No.
Well, this is particularly valuable because the A means all trig functions are positive in the first, only sine in the second, only tangent in the third, only cosine in the fourth.
Are positive.
Correct. So, if I said, so what is the tangent of 210? Well,
you know that's going to be...
The way I like to write this is I put the reference angle in parentheses, like that.
Okay.
So it's the tangent of 30 degrees, which is 1 over root 3, or root 3 over 3, rationalized. But now I still have to figure its sine. It's plus or minus sine. So what is it in the third quadrant? Is it plus or minus?
In the third quadrant, it's plus.
Correct, because it's tangent. So the tangent of 210 ends up being exactly the same as the tangent of 30. But if I said, what is the tangent of 150? Let's do that real quick. The reference angle is still 30, right? So I'm going to leave that in parentheses. So I still come up with my root 3 over 3. And then the final step is to attach the plus or minus sign. I always do these very, very methodically. You figure out the reference angle, you figure out the trig function based on that reference angle, and then you put the plus or minus sign on it.
It would be negative.
Correct, because it's second quadrant.
Right.
Now,
So only sine.
all students take calculus, but be careful. The S actually means sine or cosecant, because clearly if sine is positive, its reciprocal has to carry the same plus or minus sign, right?
Okay.
This one is tangent or cotangent, and that one's cosine or secant. In other words, secants in the fourth quadrant are positive. It's just a little harder to memorize it with all that stuff in there. So
Okay.
if we just leave it ASTC, all students take calculus, as long as you know your reciprocal functions, you'll be fine. And that's pretty much the way you can use this method to do the entire unit circle. As long as they ask you a question involving an angle that's either a multiple of 30, 45, 60, or 90, you can use this model. Well, the model doesn't work really well on the 90-degree ones. Those are called Qua Triangles.
Okay.
And the easiest way to remember those, there's a couple of ways, but ultimately...
We've memorized them, actually.
What's that?
We were forced to memorize them.
Yeah. Well, if you got it memorized, fine. What I always think the best way to do is to memorize the graph, because you need to know this graph also. In other words, part of your trig is going to be memorizing this graph. This graph is y equals sine x. And I've drawn just one period of the sine function. Well, that is pi over 2. Are you working in radians yet, or strictly degrees?
Right. No, we use radians as well.
Okay. That's pi. That's 3 pi over 2. And that's 2 pi. In other words, all of your key points occur at these quarter points, is what they're called.
Right.
And so the sine of 0 is 0. The sine of 90 degrees is plus 1. The sine of 180 degrees is 0, and so forth and so on. In other words, if you have this memorized, then you also have all of your quadrangles memorized. This will give you your quadrangles. Whereas if you just memorize the quadrangles, you wouldn't necessarily be able to reproduce this graph from memory, and you want to be able to. You haven't gotten to the part of trig yet that talks about sinusoid functions, but a big part of trig is going to be sinusoid functions, and they're all about this graph and the cosine one. In other words, okay, the cosine one you also want to memorize. It starts at 1, but has the same key quarter points. In other words, pi over 2, pi, 3 pi over 2, and 2 pi. So the cosine of 0 has to be 1. And the cosine of pi has to be negative 1. And this is y equal cosine of x. And there is another way of memorizing those quadrangles, but if you have them memorized, I won't even bother to go through that. Although it may, let's go back and look at our unit circle. Do you have to memorize the unit circle?
Not yet. No, we haven't had to. Okay,
well tell me if this sounds familiar. If that's 30 degrees, what are the x and y coordinates of that point right there? Well, it turns out the x coordinate is always the cosine of theta. So the cosine of 30 degrees is square root of 3 over 2. And the y coordinate is always the sine of theta. And the sine of 30 degrees is 1/2. So if you draw this unit circle, and it's called that because its radius is 1, no matter where you're at on the unit circle, the length of that is 1. And that's the only reason that these coordinates, I can say that's the cosine of theta, and comma, that's the sine of theta. In
Okay.
other words, a lot of trig students, almost every trig student I've ever had, has to memorize these values for your common angles, 30, 45, and 60. Not just knowing what the sine of theta or the sine of 30 is, but knowing the coordinates of that point. And instead of x and y, it's cosine and sine of whatever the angle is.
Okay.
Now, negative angles, have you dealt with negative angles?
No.
No?
Uh-uh.
Well, that's coming up too. I don't know. I'd rather we go over stuff that you're currently working on, but
Right.
I don't have any problem getting a little bit ahead. There's always an advantage to that, and that when you take your class, it'll be a lot more understandable if you and I have gone through it once.
Right. Okay, so how about this? We'll do a few of the questions that I've been working on, and then we'll get ahead, a little bit ahead.
Absolutely.
Okay, so right now we're working on trig functions. I don't have my packet with me.
Okay.
But is it possible for you to give me like a few examples?
I think so. Assuming you're referring to something like that.
Yeah.
Okay. How would we solve that?
I don't know.
Well, what if I told you x squared is equal to 3/4? How would you solve that?
If x squared was equal to 3/4,
Uh-huh.
I would root.
Take the square root of both sides.
Right.
So you end up getting square root of 3/2, plus or minus. Right?
Right.
And the plus or minus is pretty important in trig, because in geometry, you never use the minus because you can't have dimensions that are negative. But in trig, all of the trig functions can be positive or negative. So the minus solution is just as valuable as the plus solution.
Okay.
Okay? So if we do the same thing up here, we take the square root of the left side, we get sine x. So that has to be plus or minus square root of 3/2. So now the problem is solving for the angle. You've had inverse trig functions? Arc sine, arc cosine, inverse sine? In other words, inverse sine means the same thing as arc sine.
No, I don't think we've had that.
Well, probably have if you're solving trig functions, because there's no way to solve them. Let's just do a quick go by on that.
Are you talking like sine to the -1?
Yes, that's inverse sine. Okay?
Okay.
If the sine of x is equal to 1/2, excuse me, let me rewrite this. By definition, if the sine of 30 degrees equals 1/2, which it does, then the inverse sine of 1/2 must equal 30 degrees.
Okay, that makes sense.
So here's the key. We're always taking trig functions, whether it's sine, cosine, tangent, secant. We're always doing it of angles. And we're getting ratios.
Okay.
You always take inverse trig functions of the ratios in order to solve for the angles. Let me give you a specific problem where this would apply. Take a 3, 4, 5 right triangle. Everybody's familiar with a 3, 4, 5 right triangle, correct?
Yeah.
But I bet you don't know what that angle is.
No.
We're not taught that because the angles aren't the key part of this problem. but we can solve for this. In other words, if I said to you, well, the sine of that angle is 3/5, correct? Therefore, that angle has to be the inverse sine of 3/5. If you go into your what kind of calculator do you have? Is it a Inspire or a TI-84?
No, it's a pretty garbage calculator.
Does it have inverse trig functions on there?
It does.
Okay.
I think it's. Let me.
What do you get if you do you have it in front of you?
Yeah, I'm grabbing it. One sec.
Try taking the inverse sine of 0.6 or 3/5, and it'll tell you what theta is. As long as you have your calculator in degree mode. In other words, this is key that you know whether you're in radians or degrees.
What am I getting the inverse sine of?
Inverse sine of either 3/5 or 0.6.
.6435.
You might have it set in radians. Do you know how to tell? Do the sine of 30. What do you get?
Sine of 30 or inverse sine?
Well, for the moment, I'm trying to figure out whether you're in radians or degrees. So do
negative 0.98.
See, you're in radians because the sine of 30 degrees is 1/2.
Okay.
You need to switch your calculator into radian or degree mode.
Okay.
And in fact, here, I've got a virtual calculator here. Let me bring it up.
All right, now I got it where it says 0.5.
Okay, so you're in degrees. Now, take the inverse sine of 0.6. You should get 37 degrees, approximately.
0.6. It's bringing 0.010472.
Here, I'll do it on my calculator here. I'm not sure I'm hearing you. For this calculator, inverse sine is that, and that's what you're going to see. And then I'm going to do 0.6. I don't even need the second parentheses. That's in degrees. So 36.86989 is your answer. And that's that angle. In other words, if you have a 3, 4, 5 triangle, the angle opposite the 3 side is 37 degrees, approximately. In other words, you can solve for sides or angles using trig. But in order to solve for angles, you're going to need inverse sine.
Okay.
What does your class call it? Arc sine or inverse sine?
Inverse sine.
Inverse sine? Okay. Either one is fine. I'll call it that if I can remember that. Now back to the problem that I gave you. If we know the sine of x is plus or minus square root of 3/2, well, if we look at this 30-60 triangle here, I can see that it's the 60-degree angle that the sine of 60 is square root of 3/2, correct?
Right.
In other words, that you should have memorized. So what you want is where in the unit circle is the sine of that angle either plus square root of 3/2 or minus square root of 3/2. Well, there's one answer, 60 degrees. Well, in the second quadrant, that would be 120 degrees, right? In other words, if I said, what's the sine of 120, you'd say, well, the reference angle is 60, and the sine of 60 is square root of 3 over 2. It's in the second quadrant, so it's plus. So both of those are legitimate answers.
Okay.
It's minus in the third quadrant. But the equivalent angle is 240. In other words, if I said, what's the sine of 240, it would be minus square root of 3 over 2. And finally, in the last quadrant, it would be 300. The sine of 300 is minus square root of 3 over 2.
Right.
So basically, the way I got these four angles was by taking the inverse sine of this number. Another way to look at this is the following. I prefer to look at it based on by definition, but the other way is let's take the inverse sine of both sides of this equation. Well, when you take the inverse sine of the sine, you get x. Or if you take the sine of the inverse sine, you get x. Okay? So now I have x equals the inverse sine of plus or minus square root of 3 over 2. And whenever for solving trig equations, it's also important that they tell you what domain you're operating in. Now, in this case here, I was allowing x to be greater than 0, greater than or equal to 0, and less than 2 pi. That is the unit circle. So if I'm solving a trig equation, and I'm trying to find the angles, which you're almost always doing. In other words, when you have trig equations, you're always trying to find angles. Notice, there's the trig equation. I'm trying to solve for x. That's an angle. I know that's an angle because I'm taking trig functions of it. And you only take trig functions of angles. So you're usually solving for angles when you are solving trig functions. And that's why I said to you, almost certainly you've had inverse sine, because otherwise you would not be able to solve trig functions.
Right. Okay, so...
Okay, now these can get a lot more complicated. This is about as basic as it gets.
This is harder than what we're doing in class right now, actually.
Oh, okay. So maybe you have some... Go ahead.
What we've gotten in class so far is basically they'll say sine of 300 degrees.
Oh, and they just want to know what that's equal to?
They want to know what it's equal to, and they want to know the trig functions.
Well,
to solve
that's not really a trig function. What that is an expression. In fact, that's a ratio. Okay, in order to have an equation, you got to have an equal sign. So I would have to have something on the other side equals tangent of x, maybe. Now I could solve for x like that because this turns into a number, and then I can take the inverse tangent of that number. So it might be an equation, but if it's just an expression, and it sounds like it might be. In other words, if you're still in the unit circle, then they're just going to ask you tons and tons of questions of what is the trig function of this angle. So let's do that one. First, find the reference angle, which I'll put in parentheses.
So the reference angle is going to be 60 degrees.
Okay. Now find the absolute value of the sine of 60.
The absolute value of the sine.
Yeah, in other words, let's not worry about the plus or minus sign. Let's just worry about what the value is for the moment. This is a three-step process. First step, find the reference angle. Second step, find the value. What's the sine of 60? It's square root of 3 over 2. And third, attach a plus or minus sign on it based on what quadrant it's in.
Oh, okay, so it's sine, which means that it is, and it's sine and it's in the fourth quadrant, which means that it is negative.
Correct. And that's why this unit circle and everything on it is so valuable to memorize. In other words, if you memorize only one thing, make it this. Here, I'll put everything on there that you have to memorize. 180 minus theta gives you the reference angle when you're in the second quadrant. Theta minus 180 gives you the reference angle when you're in the third quadrant. 360 minus theta gives it to you in the fourth. Now, if you're dealing in radians, then this is going to become pi minus theta. This becomes theta minus pi. And this becomes 2 pi minus theta. So you don't always have to work in degrees. In other words, if they give you radians, you can still work out the problem entirely, only use the second thing. Instead of the 180 minus theta, use pi minus theta.
Yeah.
And
okay.
Finally, all students take calculus. Everything you see on the page right now is all you need to find the trig value of any angle that is one of your common multiples of 30, 45, or 60. In other words, something like 225, 300, 210, all of those angles can be done using just this information. Just it's a three-step process. In other words, I don't really, some of the school systems around Colorado, they will give you the unit circle and they want you to memorize all 16 slots of the unit circle for all 6 trig functions, which I think is lunacy because people don't memorize 16 things like that. It's not a way to get somebody to memorize something. What you do is you break it up into groups of 4 or 3. If I had a 16-digit credit card and you were going to try to memorize it, you would not try to memorize it as a 16-digit number. You'd try to memorize it in 4 groups of 4 each.
Right.
Well, that's what this picture does, is it lets you, first of all, find the reference angle, which is the equivalent of the first quadrant angle. Then you come up with the value. And in fact, to come up with the value, the only thing you need are those 2 triangles, the 2 special ones, dimensioned. Now you can come up with any first quadrant value of the reference angle. See what I'm saying?
Right.
You don't need to memorize those. You just need to memorize those 2 triangles. Now you really can. At this point, I could basically program a chimpanzee to figure out any trig function of, if I add SOHCAHTOA to the thing so that you know what sine, cosine, and tangent mean. Now you can find sine, cosine, and tangent for any of these normal angles and then use this to expand it to angles greater than 90 degrees. So if you memorize one thing, memorize what's on this page right now. Every single thing on there will allow you to answer any trig. Even if I said, what is the sine of 390 degrees? How am I going to do that?
One sec, I'm just writing. What was the question?
What's the sine of 390 degrees? In other words, greater than the unit circle.
The sine of 390 degrees. Well, you have to find the reference angle.
Well, take out as many 360s as you can.
So you can take out 1.
Right. So that's the same exact problem as that.
Okay.
Or if I said, what's the sine of 750? Well, now I'm going to take out 720 degrees and end up with the reference angle as the sine of 30. But this is a little different. These two are identical. Whereas when you talk reference angles, it's not exactly identical because the trig function of the reference angle could have a different plus or minus sign on it depending on which quadrant it's in. Whereas the sine of 750 is exactly the same as the sine of 30. I don't really need to find a reference angle, I just need to find the first quadrant angle that becomes.
Okay.
Every trig session I give to a student has this page on it. I recreate it every single time. It's what I call my Trig 101 tutoring session. And I ask every student to memorize everything you see on that page.
All right, I wrote everything down.
Okay.
I know most of it.
Go ahead.
I know most of it. I just have to memorize it.
Yeah. What the best way to memorize something like this is to see if you can create it from scratch. It's a terrible way to memorize is to have it on a sheet of paper, and every single time you go to answer a problem, you refer to the sheet of paper.
Yeah.
That sucks. You'll never get it memorized that way. That's a flaw in learning that a lot of students do. Instead of taking that sheet of paper and maybe turning it over so you can't see it, then try to do the problems and do it that way until you can turn it over all the time and know what's on it. That's the way to memorize stuff. All right. You have any other problems that you can give me?
Okay, so they gave us that kind of problem, and they gave us a reference angle problem.
Okay.
That's
Like what? Give me a reference angle problem. What? Just
Like
ask me what the reference angle is of 300 degrees?
Yes, like exactly.
Well, you've got that down pat, I think, don't you?
They did one, actually, that was find the reference angle of negative 810 degrees, and I didn't know how to do that.
So you have studied negative angles. Good. Let's cover those. First of all, a positive angle is always measured from the x-axis going counterclockwise.
Right.
So if I have a ray like that, that's a positive 60 degrees. If I start from the x-axis and go clockwise, that's a negative 60 degrees. With me?
Right.
Now, if I want to turn that into a positive angle, well, that negative 60 degrees is coterminal with that positive 300 degree angle. They're basically saying the same thing. If the ray is pointing exactly the same, regardless of whether you call it minus 60 or 300. And all of the trig functions are going to be the same. In other words, the sine of 300 is going to be the same as the sine of minus 60.
Okay.
Same with tangent, cosine, secant, all of them. Now, there is a little bit of a trick when working with negative angles that's quite useful, and that is odd and even functions. Let's start with odd function. Sine and tangent are both odd. And what that means is the sine of x is equal to minus the sine. The sine of negative x is equal to minus sine of x. So in my previous case, when I said, well, what's the sine of minus 60 degrees? Well, you could have said it's minus the sine of positive 60 degrees. We know the sine of positive 60 degrees, so it makes it pretty easy. Same with tangent. The tangent of a negative angle is the same as minus the tangent of the positive angle.
And that applies to cosine as well?
No, cosine is even. And even functions, if you take a negative value inside the parentheses, it doesn't do anything. It's the same as the cosine of x. Now,
Okay.
polynomials also can be odd or even. Why? And the way I memorize this is that's an even function, y equal x squared. If I substitute minus x for x, I still get y equals x squared, do I not?
Sorry, I'm writing.
In other words,
if you substitute,
yeah, if I substitute minus x for x and square it, I still get x squared.
yes.
Which means that f of minus x is equal to f of x. That's the definition of even. And I use the polynomial to memorize it because if the exponent is even, it's an even function. If the exponent is odd, it's an odd function. In other words,
Okay.
if I have y equal x cubed, that's an odd function. Why? Well, if I substitute minus x for x and cube it, I end up with minus x cubed. So my f of x has turned into minus f of x, which is the definition of an odd function. Now, the other thing about even functions is they are symmetrical with the y-axis. Notice my y equal x squared is a parabola, perfectly symmetrical with the y-axis. Cosine is even, meaning it has to be symmetrical with the y-axis, and it is. Looks like this. So if you have symmetry with the y-axis, you have an even function, and that's a good way to memorize it. Because it's easy to get these things. You don't use this that often, and it can be tough to memorize which one's odd and which one's even. But cosine is odd, sine and tangent are even. And it goes for the reciprocals also. In other words, if sine and tangent are odd, then cosecant and cotangent are also odd.
Okay.
Okay, so let's take your problem. What was it?
I don't remember. What did I?
Tangent of
it was no. It was find the. It was find the. Gosh, forgetting what it was. Find the
I'll make one up.
reference angle
Okay.
negative 810.
Okay, negative 810. There's two ways. If I'm merely looking for the reference angle and not the answer, then I'm going to take or add as many 360s as I have to get this thing between 0 and 360. Well,
Okay.
I can add 360, that doesn't do it. I can add 720, that doesn't do it. But if I add 1080, 3 unit circles, now I end up with 170 degrees. That's the reference angle.
170 degrees is the reference angle?
What they're really asking, excuse me, 270, sorry. I didn't do the arithmetic correct. In other words, if I'm adding 1080 to minus 810, I get 270. So that's the reference angle.
Okay.
Now, if that's all they want, that's what you do. No matter what this number is, you add or subtract. If that was plus 810, then I would have to subtract 2 unit circles, 720 worth, to get the reference angle of 90 degrees. If I want my reference angle always to be positive, then I want to add as many unit circles, multiples of 360, as I have to make this number positive. Well, as I showed, if I add just 2, in other words, if I add 720, I still have a negative number. But if I add 3 of them, 1080, then it turns it positive. And you always want it to end up being between 0 and 360. In other words, if I added too many, let's say I added 1040 or 1440, well, then I get 630. I'm not in the unit circle anymore, and I would have to subtract the 360 from that to get it down to 270. So the reference angle, always you want it to be a positive angle in between 0 and 360.
Okay.
You do whatever you have to do depending on what this number is.
All right.
Now, if the problem is what is the tangent of 45 degrees, negative 45 degrees, and they want a value for that instead of a reference angle, well, first of all, I can find the reference angle. What's the reference angle?
The reference angle is
what multiple of 360 do I need to either add or subtract to that?
360.
Okay, what do I get?
315.
Okay, so that's the reference angle. And now I'm tasked with figuring out what the tangent of 315 is. Ooh. And the reference angle is 45 degrees. In other words, I did this in 2 steps, okay? I was wrong. 315 is not the reference angle. 315 is merely coterminal with minus 45, meaning a multiple of 360 away from, okay, added or subtracted to it. Once I get this, now I have to find the reference angle, which is 45 degrees, and then go through and figure out the tangent of 45 degrees. Know that I'm in the 4th quadrant, so it's going to be a negative. Well, the tangent of 45 degrees is 1. That says 4th quadrant, so it's negative 1.
Okay.
But notice that it's faster if I use the odd and even properties. In other words, if I really want to know what the tangent of minus 45 is, I don't need to go through this process of finding this angle and then the reference angle. I know immediately that that's the same as minus tangent of positive 45. Well, I know that's 1, so I know it's minus 1 instantly, and I never had to deal with 315, the number.
What is minus tangent?
I'm sorry, what?
What is minus tangent?
Well, first of all, trig functions are taken of angles to give ratios. So they can be plus or minus.
Okay. So you're kind of just...
I understand why you would ask the question, because tangent, if tangent is opposite over adjacent, how is it ever negative? But
it's like an absolute value sort of thing. You apply the negative afterwards.
Right. In other words, notice what you're looking at here. Is all I've done is taken the negative outside of the parentheses and put it in front of the function. If I had cosine of minus 45 degrees, I would use the fact that that is an even function to know that that's the same as the cosine of 45. Instantly, square root of 2 over 2. Positive square root of 2 over 2. As opposed to finding out, well, that's also 315, which gives you a reference angle of 45. We're in the 4th quadrant, so we get positive. it's quicker to use the odd and even property to actually figure out these negative angles.
Okay.
There's
Cosine
two ways to
even
do them. There's using the reference angle, and there's using the odd or even property of it.
right.
The odd or even property saves one full step, always.
And cosine is the only even one you said, right?
Yes. Sine and tangent are odd. And
what about
go ahead.
What about secant and cosecant?
They're the same as their reciprocal. In
Okay.
other words, since secant is the reciprocal of cosine, it's also even.
Okay.
Since cosecant is reciprocal to sine, it's odd.
Okay.
In reality, the odds are sine, cosecant, tangent, cotangent. The evens are cosine and
cosecant. And secant. And cosecant, so that looks like 1 over sine?
yes, precisely.
Okay.
And those are very important. That may be more important to memorize than my unit circle, is those reciprocal relationships.
And tangent is sine over cosine, so it'd be 1 over sine over cosine.
Let me give you an easy way to memorize these. Really easy. We have our 3 primary. What's the reciprocal of tangent going to be?
Cotangent.
Which means we only have to figure out whether sine goes with secant or cosecant, because the other one will go with the other one. Well,
right.
I know it goes with cosecant, and I know that because each of these pairs has exactly 1 co in it. There's the co in that pair, there's the co in that relationship, and there's the co in that relationship.
Okay.
So if you ever make a mistake and say sine is 1 over secant, there's no co there. So that can't be right.
And yeah, my teacher told me S goes with C, C goes with S.
Okay. Yeah, I like that too. Yeah, I like that. Yeah. There's all kinds of ways to memorize stuff, whatever works best for you.
Okay, so that's actually a really easy one to remember. 1 over cosecant and all that.
Well, and this also implies the reverse. In other words, if sine is 1 over cosecant, then cosecant's 1 over sine.
Yeah.
So there are 6 reciprocal relationships that you need to memorize, all 6 of them. But you really only need to memorize 1. That one right there. Because once you get this one, you can figure out this one, and you can figure out that one. And then you can figure out the other 3.
Right.
Now you mentioned your Pythagorean, we went over the Pythagorean identities, and there's 2 other that are really valuable. There's 11 identities that are pretty much must memorize for anybody. There's 6 reciprocals. We just talked about those. There are 2 quotient. The quotient identities are tangent is what?
Tangent is sine over cosine.
And the other one, you only have to memorize that one because the other one is the cotangent, which must be what?
1 over sine over cosine.
Or cosine over. You don't need the 1.
Okay.
Okay, in other words, when you have the reciprocal function, you can just flip whatever that is.
Okay.
You get it, okay? And then finally you have your 3 Pythagorean identities. And as I said, the only 2 that you have to memorize are this one and this one. Because the other one you can figure out, it is the co-function. Now, before I leave, I want to distinguish between cofunctions. In this reciprocal, in teaching you to memorize these reciprocals, I said there's exactly one co in every relationship.
Right.
Well, there's also something else in trig called cofunctions. The cofunction of sine is cosine. In other words, it's whatever the word is with co in front of it. The cofunction of tangent is cotangent. And the cofunction of secant is cosecant. And cofunction properties are different. We haven't even talked about those yet. But the only reason I bring this up is don't mistake this for the reciprocal relationships. In other words, these also have exactly one co in them. There's the co there, there's the co there, and there's the co there. But they're nothing like the reciprocal. The only one that's the same is tangent. The cofunction of tangent is cotangent, and the reciprocal of tangent is cotangent. But that's
these are exact opposites, aren't they?
What's that?
These are exact opposites, aren't they?
No, what this means is that the sine of x is always equal to its cofunction of 90 degrees minus x. You'll notice that the sine of 30 degrees is the same value, 1/2, as the cosine of 60 degrees, always. Same thing, all three functions. So cofunctions have this property, which is nice. I mean, you might need that at some point. I suspect they haven't really got to cofunctions yet in your class, but the only reason I mention it is it's because of that word co, it's easy to get confused with the reciprocal relationships, especially when I say the reciprocal has exactly one co in it. Well, so do these. So it's easy to get mixed up. And these also work in reverse. In other words, the cosine of x is also equal to the sine of 90 minus x.
Okay.
No matter x.
All right.
So all trig is about is memorizing, really. Almost. You can almost say that's exactly all that it's about. It gets more complicated than that, where you have to
apply. Yeah,
apply it. But in the beginning, trig is basically memorizing and trying to figure out a way to memorize everything.
It's what a fun topic.
Actually, I love it. I love trig. And you're going to be amazed at how vital trig is for higher mathematics. Calculus would be impossible without trig. It makes it so much easier and doable. And trig is just fundamental to all math that's higher than trig. So it's kind of like a foreign language, really. You know, these words aren't English words, they're trig words. One thing I wanted to ask you, Max, is there's a balance of 120 due on your account. I've sent an invoice to your mom. Is that the right email address? robin.brenner@yahoo.com?
Yes, it is. She's terrible at checking her email. I'll tell her about it.
Okay. So after today, that would be 152.
Okay.
Okay?
All right.
And I'll send her another email as a reminder. And I'll send it to both of you.
All right. Thank you.
You're welcome. Max, have a good one. Talk to you next time.
All right. You too.
All right. Bye-bye.
Bye.